Hi, my name is Elena, and I was one of the RU students this past year, and I'm presenting my research on probability of recombination types in the ancestral recombination. So this is the mathematical way that we generate the ancestral recombination graph. It's called the SMC prime algorithm. The first thing we're going to do is look at this chromosome to the bottom left. We're going to set x as 0 as the original distance on the genetic material and generate a coalescent tree there. So each step on this chromosome will have a brand new coalescent tree, and we are going to generate y, which is the distance until the coalescent tree actually changes in some way. So that'll be an exponential distribution, and the parameters there depend on the recombination rate and the length of the previous tree. So that will be the distance along the chromosome until the next recombination event. Then, to actually place the recombination event, we're going to look at the coalescent tree at that point and choose a point G uniformly at which the recombination event will occur in the tree. So to add that recombination event, we're going to create a branching point. It'll be looking upward, and that means it will look like this instead of like this. And we will delete the left part of the emerging branch to maintain the tree structure. And then we will start the process over, looking back toward the chromosome by setting a new x to be the previous x plus y, so that we are sort of starting at the point we left off on at y. And then we will generate a new y with the same parameter. Until we get to 1, which is the other end of the chromosome, and this is actually the fastest and most accurate approximation of the arc, so this is what is used often in computational biology now. So this is the final result. It's going to be a coalescent that has the same tree up until y, and then at y the tree changes in some way, and then at y the tree will change in some way again. So there are many different approaches to classifying these recombination events that, as we saw, will change the structure or the length of the tree. This is the classification that we use in our project. So type 1 will be no change, and that is the beginning and ending of the arrow representing the recombination event happens on the same branch. Type 2 occurs when the two branches that represent the starting and ending points of the recombination are only one coalescent event, or like T shape, away from each other. And type 3 occurs when there are two or more T-shapes away from each other. So a length change will produce pretty much what it sounds like, either a taller or a shorter tree, and a topology change will produce sort of a different branching system, a new branch, deleting an old branch, something like that. And the goal of our project is to produce an estimate for the expectation of the eventual length of this tree after undergoing like a long-term set of these recombination events. So to do so and to look at those cases, we took a really simple example, which is the two-leaf n equals 2 case. You can see that there are only two nodes at the bottom of the graph. That's why we name it that way. And in this case, there are only three subtypes of recombinations. Those are lengthening, shortening, and no change. You can see the topology change event is not represented at all because there are not two branching events, T-shapes, to go past. So in this case, the recombination begins at one branch and ends on a completely different branch, one T shape away from each other, but in this case, the recombination event ends above the branching. That's represented by the single line graph to the right, and the A and B represent the range that the new length L1 can be within. The same sort of event takes place in shortening, except for the new length is below the branching point, still one branching point away, but below this time, and that's represented again by A and B, which represent the possible area of that length change. The same goes for the no change situation, where they're represented by A and B, which represent range. But in this case, L1 actually takes place on the same branch as where the recombination event began. So this is the formula that we used to represent the probability of the new length L1 being within the range A to B, given the original length L0. This was derived from the idea of a non-homogeneous Poisson process, because that rate, lambda r, does change depending on where you are in representation to the branching point. Thank you so much to the IURU program, and to you for listening. Thanks.